Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So now we have a new problem with us. The problem says that given a non-negative integer value n, you need to calculate the nth Fibonacci, right? The value of n is given as 5. Then the answer should be 5 because the fifth Fibonacci is 5. And if the value of n is given as 8, then the 8th Fibonacci is 21. We have to do it recursively. That is the interesting part. Now, everybody might be already aware about Fibonacci, calculation of Fibonacci using normal iteration. You can maintain 2-3 variables and achieve that. But the core crux of the problem lies behind the fact that what is a Fibonacci? If you look at a Fibonacci, 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. This is the Fibonacci numbers. This is the 0th Fibonacci. This is the first Fibonacci. This is the second Fibonacci. Third Fibonacci, fourth, fifth, sixth, seventh, and eighth, and so on. So these are the Fibonacci numbers. The core, I would say, observation that you can find in a Fibonacci number is that if you carefully see any Fibonacci number, it is the sum of the previous two Fibonacci numbers. 3 plus 2 leads to 5. 2 plus 1 leads to 3. 5 plus 3 leads to 8. 8 plus 5 leads to 13, and so on. And these two are the seeding values or the base values because there is nothing behind them. So we have to remember that the 0th Fibonacci is 0 and the first Fibonacci is 1. Rest all of the Fibonacci number can be computed by the sum of the previous two Fibonaccis. You can see any Fibonacci. For example, 13 is computed by. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different. And a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Sum of 5 and 8. This is the property of Fibonacci. So any ith Fibonacci can be computed using the sum of I minus 1th and I minus 2th Fibonacci. This is something really standard that they can be achieved by the sum of I minus 1th and the I minus 2th Fibonacci. Right. Now we have to implement it recursively. If we have to implement it recursively and we somehow, let's say, write a function f of n, we somehow write a function f of n that returns us the nth Fibonacci. Right. And I don't know how to calculate this function. But let's say if somehow I assume that the function f, which has to calculate nth Fibonacci, I don't know how to implement it, but we assume that the function f works correctly for n minus 1. Assume f returns n minus 1th Fibonacci correctly. Right, we are going to assume this, and we are going to make one more assumption. So sometimes you can make 2 or 3 or more than that assumptions also, that if f of n minus 1 is computed correctly, as well as f of n minus 2 is also computed correctly. What is f of n minus 2? Assume f returns n minus 2th Fibonacci also correctly. Right. So we are assuming this. We are doing an assumption that if somehow I want to calculate, the problem given to me is to calculate the nth Fibonacci, and somehow, somewhat, if somebody can give me the correct answer of the n minus 1th Fibonacci and the correct answer of the n minus 2th Fibonacci, I can just club them up, I can just sum them up and then calculate nth Fibonacci. So my own task is going to be what? To sum them up. This is going to be coming from assumption that we assume that the n minus 1th Fibonacci works correctly, right? The function f is computing the n minus 1th Fibonacci correctly, and the function f is computing the n minus 2th Fibonacci correctly. The only agenda that we are left with is to sum them up, right? So this summation is going to be our self work. Summation is going to be our self work, and that's it. If you talk about the base case, that is what is the most trivial value of n, for which we already know the answer, then can I say for n is equals to 0, the answer is 0, and for n is equals to 1, the answer is 1. These two can be the base cases. That if somebody gives you n as 0, return them 0. If somebody gives you n as 1, return them 1. That is it. So this is the recursive relation that we have formed for Fibonacci. And if you want to code it, I'll be coding it as it is, and everything will be done. So first of all, I'll be coding it, right? Then I'll show you a deeper analysis around the overall recursion structures and the debugging of Fibonacci. We'll talk about a few more things. But first of all, let's establish this fact that if we are writing these relations properly, we don't need to make any coding effort as such, right? If you want to code this solution, what you can do is you can write a function int f. It is going to take a value int n. You can see f of n we wanted to implement. First of all, base case. If n is 0, you return 0. If n is 1, you return 1. Can I say that? Now when n is 0, you are returning the value n only, like 0. When n is 0, you return 0. Same for n is equals to 1 also. When n is 1, you are returning 1. So technically I can club both of these. I can say if n is 0 or n is double equals to 1, I can return n, right? Because if n is 0, I want to return 0. If n is 1, I want to return 1. Otherwise, what is the relation? We will return f of n minus 1 plus f of n minus 2. That's it. We are done. If we talk about the fifth Fibonacci, you can see fifth Fibonacci is 5. If we talk about the eighth Fibonacci, that's 21. Right? So this basic Fibonacci recursive logic is working fine, and we are able to calculate the nth Fibonacci in just like 2 lines of code. I hope this point is making sense to everyone. Now let's try to code Fibonacci for us. So we'll say, just a second. I had a Java extension installed, I believe. It should autocomplete, right? Strange. Okay, I'll take a look at it later. For the timing, I'll just recreate the file. Delete. New file. Fibonacci.java. Okay, yeah, it has automatically created it. Now, I'll public static void main. Here we go, right? And now I'm going to write a function. You will always find me doing this. Whatever I write in the recurrence relation, I want to make always this thing same. So what is the name of the function in the recurrence relation f? I'll just write a function public static int f. Why int f? Because it will be an integer value that it will return in the form of Fibonacci. Okay. Now, what is the parameter? N. And why I took n? Because to calculate the nth Fibonacci, logically also, if you see, to calculate any nth Fibonacci, you just need n minus 1 and n minus 2. So in order to identify a sub problem, see, it identified these two as a sub problem. In order to identify a sub problem, we just need the value of n. That is the power of recurrence relation. You always have to figure out that if you want to write these recurrences, right, this is a bigger problem. These are two smaller sub problems. We have to always figure out that, first of all, in order to write a sub problem, how do we identify a sub problem? So we identify the sub problem based on the parameters, which are actually changing, right? So here you can see the only parameter that is required to identify a problem is n. Okay. And what is the value of f of n? The value of f of n is, we should return f of n minus 1 plus f of n minus 2. That's it. Okay. This is the recursive relation. So you did the recursive assumption that go and calculate n minus 1, go and calculate n minus 2. I'll sum them up. Base case. What is the base case? If the value of n is 0, that is f of 0, you return 0. If the value of n is 1, you return 1. That means if n is equals to 0 or n is equals to 1, you return n. See, if n is 0, you have to return 0, so return n. If n is 1, you have to return n, that is you return 1. And that's it. You can see very simple implementation we have. And whatever I said, I just wrote it. This is the recursive relation. And before that, I already told you that we write base cases. And now, if let's say want to calculate 6 Fibonacci, run it. Okay. Let's see what happened. Okay. I believe we can remove this package for now. We don't need this. Okay. And okay. See, we are getting 8 here, right? As simple as that. And 8 is what? The 6th Fibonacci. If you get a value as 5, see, you're getting 5th Fibonacci, right? As simple as that. So this is what we have to do, right? Now what I'll do is I'll do a quick dry run. And why do I want to do the dry run? Because this is the first recursive problem where we have seen that any problem is dependent on not one, but two sub problems, n minus 1 and n minus 2. It is dependent on both. If you see the previous set of problems, here f of n was dependent on n minus 1. Here also f of a comma b was dependent on a comma b minus 1. But here, this is the first time when a problem is dependent on two subproblems, and that definitely we would like to actually dry run. So till now we have done three problems on recursion, right? In every problem of recursion, we write the base case first. Now, a lot of questions might be coming to your mind that why we are always writing the base case first? Why not base case is written somewhere else? So let me answer that. 99% of the time, you are going to write your base case first. There is a reason for that. Why there is a reason for that? Because we need to make sure that whenever our function, our recursive function hits this condition of the trivial case or the base case, we need to terminate that. We don't need to do any computation. There is no computation required. If there is no computation required, we can just immediately return the answer. Because base case technically act as a terminating condition, right? So these terminating condition needs to mentioned in kind of like the first line or the first 2-3 lines of the code only, so that we can avoid any kind of computation. Because if you will go beyond these base cases, then you might never find your answer, because these base cases are the smallest possible problem, and for these smallest possible problems you already know the answer. That is why we write the base cases first, so that you avoid any kind of computation and anyhow avoid any kind of recursive calls, because any recursive calls beyond these base cases can become disastrous, because then there won't be anyone to stop them. So these base cases are technically terminating conditions, and that's why we put them at the top of our code. So I want to talk about one more interesting thing. If you see all of the codes that I have written till now, I'm doing something like n minus 1, b by 2, n minus 2, n minus 1, right? Nowhere I'm doing n minus minus or minus minus n or something like that, right? Every time I'm doing n minus 1. And it is always recommended that you avoid any kind of unary operator here. Why? Just think about it in terms of factorial. If instead of this you write factorial like this, return n into f of n minus minus, you might feel like, okay, this is also going to do n minus 1, but technically it is not. What will happen is n minus minus, this is a postfix operator, right? So the value of n will be used first, and then we are going to do minus minus, right? So n will be used first. What is the value of n? Let's say the value of n is 5. So technically in the function f, you are going to pass 5 only. You are not going to pass 4. You are going to pass 5 only, right? So technically from f of 5, you are going to f of 5 only. Then f of 5, again from f of 5, you go to f of 5 only, because this value is going to decrease when the function is computed, right? That's why we never do n minus minus. Similarly, using something like minus minus n is also not recommended, because currently in all three functions, we have just returned immediately. But sometimes you might not have to return immediately. You might have to do some more computation. If you will do minus minus n, then technically this will update the value of n in the same function call from 5 to 4. In the same function call, it will become 5 to 4. So it can also lead to some confusing cases that you might have not thought about encountering earlier, and now you are encountering. That's why the best practice is to use something like n minus 1, because this doesn't change the value of n at all. It just at runtime computes a new value n minus 1 and then passes that to the function f. It never changes it, and it never actually changes the value of n. So we never mutate the input. That's why we are kind of like safe. So that's why you most of the time you will never find people doing b divide equals to 2 or n minus minus n minus equals to 2. All of these operations are never done in a recursive function. Now let's try to actually do the dry run of this Fibonacci, right? Along with the dry run, I'll also show you the course of execution of the functions, okay? So let's say we are going to call for f of 3, okay? So from the main function, I'm going to call for f of 3, okay? Cool. So if I draw it here, f of 3, we are calling f of 3, right? So here the value of n is 3. Value of n is 3. You are going to check. In line number 2, you are going to check, is 3 equals to 0? No. Or is 3 equals to 1? No. So this if check won't be executed. You go to line number 3. In line number 3, you have two function calls. So technically you need to compute two function calls, and the result of the two function calls is going to be your answer. So first of all, we are going to call f of n minus 1. So we are going to make an entry for f of n minus 1. What is n? N is 3. What is 3 minus 1? 2. F of 2. So technically speaking, from f of 3, you made a call to f of 2, right? And this function call is waiting on line number 3. Can I say that? It's not like you have made a call to f of 2 and f of 1 parallelly. See, currently we are just at f of 2. We will compute f of 2 first completely. That is this part. We are computing this part. Okay, cool. Now we are at f of 2. N is equals to 2. We go to line number 2. Is 2 equals to 0? No. Or is 2 equals to 1? No. This if check is not going to work. Can I say that? Right? We go to line number 3. In line number 3, again, two function calls are expected to be computed. We will leave this function on line number 3 and call for f of n minus 1. N is 2. What is 2 minus 1? 2 minus 1 is 1. So from here, we made a call to f of 1. See, we are making a call in one direction first. It's not like we are parallelly making everything. We are making a call one by one. Here n is 1. Now, is n equals to 0? False. Or is n equals to 1? True. N is equals to 1, right? That means we are going to return n. Can I say that? We'll just very quickly return the value of n. If we return the value of n, we are going to return it here, right? So we return the value of n as 1. So 1 is returned here, right? So you return the value of n as 1. Okay, we returned the value 1. And because we have returned, this function call is going to be removed. You are back on f of 2. You are back on f of 2, which you left on line number 3. On line number 3, you computed the first expression successfully, which was 1. Now there is another function called f of n minus 2. See, we have to compute this, right? F of n minus 2. So we'll make another function call to f of 2 minus 2. What is 2 minus 2? F of 0. So from here, we are making call to f of 0, right? Now, here n is equals to 0. You check. Is 0 equals to 0? True. You don't even need to check this. You are going to return n. So from here, I'm going to return a 0. And because I have returned, this stack frame will be removed. Now you are back on f of 2. You are back on f of 2 with a value 0, right? On f of 2, you left f of 2 on line number 3. And now both of the function calls have been computed. All you have to do is just add up them. 1 plus 0 is 1. And then return them. So I'm going to return 1 from here. So technically, we are going to return 1 from here. Right, and because we have returned, this function call will be removed. Right, and you are back on f of 3. You see, when we started from f of 3, technically from f of 3, we need f of 2 and f of 1 both. But we first went and compute f of 2 completely. We are not parallelly computing f of 1. This is the essence of this algorithm. It's not a parallel algorithm. We first of all go in one direction, come back and then go in the next direction. So now you are back at f of 3 with a value 1, right? You left f of 3 at line number 3. At line number 3, you computed this. You're still left with one more function call. So I'll make this function call f of, what is 3 minus 2? 1. F of 1. So n is 1 here. So we are now making a call to f of 1. You check. Is n equals to 0? No. Is n equals to 1? Yes. You return n. So I'm going to return a 1 here. And because I have returned, it will go back. Now we are back at f of 3 because this function call also returned a 1. So at line number 3, we have 1 plus 1. So we'll add them up 2 and then return. So 2 will be returned. and this function call ends, right? And that's it. And that's it. The value of f of 3 is 2. So you are able to see that we are not making calls parallelly. And this tree, the order in which this is kind of like a hierarchical structure, right? It's kind of like a tree-like structure. This tree is called as a recursion tree. To visualize recursion tree helps us a lot, right? So you can see in this tree also, we just go to one branch completely, come back, then go to the next branch of the tree and so on, right? This is something which is very important for you to understand. A lot of people have this notion in the mind that all of the function calls goes parallelly, but it's not the case. That is why when we talk about the space complexity is not going to come due to every function call, because from f of 3 you to go to 2, then you go to 1. Maximum space that you are going to take is only 3 stack frames, because the moment f of 1 comes back, this stack frame is removed. That's why to visualize space complexity, we need to see how long one branch can be, right? When we'll solve more problems, you will get a hang of it. But I hope this basic part is making sense to everyone. Let's do one more dry run for f of 4, right? So from the main, we are going to call for f of 4. The main is the first function in the stack frame, okay? So technically we are calling for f of 4. So the first stack frame we added for is for f of 4. So n is equals to 4. You will check. Is n equals to 0? No. Is n equals to 1? No. So this if check will not be executed. You go to line number 3. On line number 3, you have two function calls whose result do you expect, right? The first function call is f of n minus 1. So let's make that function call. So we are going to leave f of 4 on line number 3 and we'll say 4 minus 1, that is 3, right? Why? Because n was 4. If you call for 4 minus 1, it will make a call to f of 3. F of 3. Okay. Cool. Another stack frame with n is equals to 3. Is n equals to 0? No. Is n equals to 1? No. So the base case also doesn't exist or execute. Then again you go to line number 3, right? In line number 3, we write two function calls. We need the answer of both the function calls. The first function call we will go first, that is n minus 1. So we'll technically make a function call to f of n minus 1. What is 3 minus 1? 3 minus 1 is 2. So you make a call to f of 2. Okay. And this function is also waiting on line number 3. You go to f of 2. The moment you go to f of 2, n is 2. You check. Is 2 equals to 0 or 1? No. Again, if base case won't be executed, you are again on line number 3, which expects two function calls. First function call is for n minus 1. What is 2 minus 1? 2 minus 1 is 1. 2 minus 1 is 1. So you make a call to f of 1. Now f of 1 is a base case. You see, is n equals to 0? No. Is n equals to 1? Yes. So you return n. So because this was a base case, I'm going to immediately return 1 from here. So I'm going to return 1 from here, right? And the moment I returned, this stack frame is going to be removed, right? Okay. We are back on line number 3 of function f of 2. So we are back on this function call. The above function call is done. We are back on this function call. In this function call, we were on line number 3, where we computed the first f of n minus 1. Now we need to go to the second call, f of n minus 2. What is 2 minus 2? 0. F of 0. And again, this is a base case. Is n equals to 0? Yes, you return n. So technically, we are going to return 0 here. So this will be returned as 0 and this function call ends. Now you are again back on f of 2. See, you are back on f of 2. Both of your function calls have been computed. Now the only instruction left is to add them and return. What is 1 plus 0? 1. And you will return them to the call state. Right. So from here, I'm going to return 1. I'm going to return 1. Okay. We are back on f of 3. See, we are back on f of 3. The first function call of f of 3 has been computed. Let's go for the second function call. The second function call should be n minus 2. What is 3 minus 2? 1. So you're going to make a call to f of 1. So from here, we make a call to f of 1. Right? F of 1 is a base case. N is 1. So you return n. So this also returns 1. So we return a 1 here. And that's it. We left this function call f of 3 on line number 3, where both of the functions have been computed, 1 plus 1. All you have to do is just sum them up and return. What is 1 plus 1? 2. And then you return 2. You return 2, right? Okay. So now f of 4 went to one particular branch and computed f of 3. And you know the value of f3 is 2 and we are correctly computing it. Now what will happen is f of 4 is back and we were on line number 3. We have computed one function, but the other function is still left. So we'll make a call to f of 4 minus 2. What is 4 minus 2? F of 2. So technically we're going to make a call to f of 2. Right. Then is 2 equals to 0? No. Is 2 equals to 1? No. So we'll say again 2 more function calls. We are going to leave it on line number 3. First function call. What is 2 minus 1? F of n minus 1 is 2 minus 1. 2 minus 1 is 1. So we are at f of 1. F of 1 is a base case. See? We are at f of 1. F of 1 is a base case. You return n. So from here you are going to return 1 only. From here you will return 1 only. And back on line number 3. We are back on line number 3. And on line number 3 we have one more function called n minus 2. 2 minus 2 will be 0. F of 0. Right? F of 0. And f of 0 is a base case. N is 0. Base case. So you are going to return a 0 from here. And we are back on f of 2. And we are back on f of 2. Now f of 2 we left on line number 3. Both of the functions are computed with a value 1 and 0. What is 1 plus 0? 1. So you are going to return 1 here. And that's it. Now f of 4. F of 4. We are back on f of 4. And this time both of the function calls have been computed. What you would do, what you are expected to do, you just add them up and return. So what is 2 plus 1? 2 plus 1 is 3. And we are going to return 3. And that's it. We are back in the main function. So this was the dry run for f of 4. And this is the recursion tree that will be actually, you can prepare a mental model based on this recursion tree, that how all the calls are actually made. And I hope this basic dry run is clear to everyone. Now, one very crucial piece of information that you can observe here is that this f of 2 is getting computed 2 times. Technically, this is not the best way to go for, right? We are, the moment f goes beyond a scene like f of 10, f of 20, f of 30, there will be a lot of repetition. So in order to avoid repetition, we can save up calls, we can store them. For example, in the power function also, we stored the power function call somewhere. This technique is specific and it is have a particular name. We are going to talk about it later. But first of all, in this stage of recursion, our first agenda should be to solve problem in some manner so that we can get a hang of recursion. After that, we are going to start the optimization part.